So it's all well and good to be able to use parallel streams and at least ideally make your program run faster if your n times q model plays out appropriately. However, you need to be aware of some programming hazards to avoid chaos and insanity. So we're going to talk here about some of the common programming hazards in Java parallel streams and, of course, how to avoid them. So it's not just enough to know that there's problems, but we also want to solve the problems as well. And one of the things we're going to talk about is hazards that stem from the use of stateful lambda expressions that are not properly synchronized. And then we'll also talk about hazards that are introduced from interference with the data source, which is very, very subtle and easy to get wrong if you don't have a deep understanding of how things are working under the hood. So let's start by talking about a couple of assumptions. The Java parallel streams framework assumes that the behaviors you pass to intermediate operations don't incur race conditions. And recall the definition of race condition. A race condition arises when an application's behavior, correct behavior, depends on the sequence or the timing of the threads in order for it to operate properly. So if you get lucky, it'll work. If you don't get lucky, it won't work. It'll give you very, very strange results. The common way to deal with this is to avoid, or at least minimize, but better avoid, behaviors that have side effects if you're programming parallel streams. And we've seen some examples of this already, where you make sure you use stateless lambda expressions or method references and so on. And then that problem just sort of goes away. If you can't do that, then at least make sure that the behaviors you pass in are properly synchronized with respect to concurrent execution, which is usually not that hard to do because Java has tons of mechanisms for doing synchronization, like concurrent hash maps or reentrant locks or stamp locks and so on. But you just have to be aware of that. Second problem, hazards with stateful lambda expressions. So let's take a look at some examples here. This is a fun example where the results depend on shared mutable state, and this gets us into trouble. So this is a buggy factorial example, and you can see it here in my EX16 project, in my Java 8 folder, in my live lessons GitHub repository, and this illustrates what goes wrong. And here's the source of the problem. We have a class that's called mult, and it's got a variable, which is mlong of type long, and you can see here that the multiply method is going to do the multiplication and update of mlong by the parameter mult mlong, which is of type mult. And this will work perfectly fine if you're in a sequential stream, but the moment that there's a parallel stream, then this becomes the dreaded shared mutable state that's not protected by any synchronizer. And so as a consequence, chaos and insanity will ensue. So here's the situation where this can occur. So we have a method called factorial that takes a long n, and we're going to basically create a range of values from 1 to n, inclusive. We're going to run this thing in parallel, and then we're going to go ahead and do map to obj using this new mult thing we looked at over here. But you can see that it's going to have this single instance. And so as a consequence, race conditions may occur here due to the unsynchronized access to the mlong field in mult. So you can see reduced, we say new mult. So we got one and only one instance of this thing. And now we're going to be calling the multiply method as the accumulator here in reduce, but it's always going to be accumulating into mlong. And since multiple threads are calling multiply and mlong is not protected, then crazy things occur. And what's interesting here is even though we're using the reduce terminal operator, we still are going to have problems. So this is not going to save us. Why is this not going to save us? Because reduce expects to have mutable objects, reduce expects to have immutable objects, and we've given it a mutable object that will update itself because you can see here this is going to allow mutation. So there's just all kinds of things that are going awry in this case, and we need to be very careful to avoid falling into this sort of trap. So how could we avoid this problem? Well, one trivial way to avoid this problem is to get rid of the use of reduce with this crazy mult intermediate class that has this dreaded shared mutable state mlong field, and instead do what reduce really wants, which is create immutable objects, like in this case, passing in 1L, and then going ahead and using a lambda expression that takes immutable objects and creates a new mutable object. And that will work perfectly fine when run in a parallel program. So just a couple things to remember about shared mutable state with streams. It doesn't like it. It works weird. Another way to fix this problem, by the way, would have been to go over here and make multiply be a synchronized method, in which case we wouldn't have to worry about synchronization and unsynchronized access to shared mutable state. The downside with that approach is that now we're synchronizing out the wazoo, and that will actually most likely be more expensive in terms of overhead than this technique. And in fact, if you want to prove that to yourself, you can run the examples in the EX16 project, because I also have an implementation that uses synchronized methods, and it times the results, and you can see they're much slower than using reduce in this form. Next problem I want to talk about is hazards that are introduced from interference with the data source. So what the heck does that even mean? This occurs when the source of the stream is modified within the pipeline, within the various elements that are chained together in a fluent style. So let's take a look at this. So this example is from my EX11 project in the Java 8 folder in the Live Lessons GitHub repository. And what it's going to start out by doing is it's going to make a list of 10 integers in the range 0 to 9. So here we have range 0 to 10. This is not inclusive, so we don't include 10, so it's basically 0 to 9. We take each of those integers, we box them, and then we collect into a linked list. So we now have a linked list as the implementation of the list. Then what we do is we say list.parallel stream, so run in parallel, and then we're going to do something really gnarly and horrible. We're going to use the peek operation, which usually is used for debugging purposes, just to log something. It's not supposed to modify anything. But in this case, just to be completely pathological, we're going to pass in the list remove method, which will start removing items from the list that we're trying to iterate over and print the results out. And all kinds of things will go wrong here. So first of all, this is a non-concurrent collection. Linked list is a non-concurrent collection. It's being modified while it's being operated on in the parallel stream, and just crazy, crazy results will happen. So if you want to amuse yourself, try running the example. You'll see what it does. It dies a horrible death very quickly. So do not do that. So how do we avoid these things? Well, we want to try to have no side effects if we possibly can. We want to use lambda expressions and method references that are so-called pure functions. So here's a good example of this, where we've got search for phrase, and this is a pure function because it doesn't have any state that we have to worry about. We can use search results is empty, and we can negate it. That just returns mlist.size. That's not going to be modifying anything. It's just reading stuff. This is creating stuff, but it's doing it in a way that doesn't have side effects. If you have to have stateful behaviors, if there's no way around it, like, for example, our image cache that we have for our programming assignment, then make sure that you properly synchronize things. And the easiest way to do that, often, depending on what you're dealing with, is to use some kind of concurrent collection, like a concurrent hash map or a concurrent linked queue or whatnot. And if you are interested, concurrent hash map, we don't really cover that much in this course other than just mention it exists. In my other course, which you can take a look at online, you can learn about that. Concurrent hash map has some really cool features that make it not only thread safe, which is key for this type of purpose, but also very efficient. And so what it does is it basically has locks for each of the buckets in the hash table. So if you recall how hashing works from CS 2201, we'd have a hash table, which is an array, and there will be, coming off of each element wherever something hashes to, there'll either be a linked list to resolve collisions or a balanced binary tree, depending on various circumstances. In either case, they use a very clever locking technique known as a compare and swap operation. So whenever something hashes to a location, then there's a compare and swap operation, which is super lightweight for synchronization, and it will then go and put the element, either put it in the list or the tree, or remove it, or look it up, or whatever. And if you have multiple things that are mapping to different elements in the hash table, those will all run in parallel because they each have their own compare and swap lock, using the word lock loosely, synchronizer is a better word, in order to be able to have things running at the same time. And they also do a lot of other cool things, like if you're reading, they don't have to worry about modifying anything, so they can treat the reads as an optimization, and things can go in parallel, even if they end up hashing to the same location. It's only if they write that you have to be careful, but even there it can be handled quite efficiently. So if you want to learn more about concurrent hash map, I'll be happy to show you other videos. There's some nice discussions that appear in various web sources that will tell you how it works under the hood. It's really cool. Or you can look at the source code, which may be a bit more mystifying, but it's pretty interesting. Okay, so that's the end of our discussion of avoiding programming hazards with Java parallel streams. Mercifully, for the assignments you're doing here, you don't have to worry about this because we've kind of abstracted away a lot of the details. But if you write your own code, just be aware that you can get yourself into trouble if you don't think about how stuff works under the hood.